Thank you for joining. I will present joint work with Alessandro Killer and Aditya Golatkar at UCLA. And specifically, we'll introduce a notion of reachability of learning tasks, which formalizes whether you can transfer information from one task to another. Better yet, it quantifies how easy or difficult it is to transfer from one task to the other, which is a question relevant to transfer learning, domain adaptation, continual learning, curriculum, or lifelong learning. So why do we need a notion of reachability in the first place? Why not just a distance? Isn't it enough to know how close two tasks are to determine whether I can transfer one from the other? So I will give an example of two tasks that are close in any sense that you can imagine, and yet if you pre-train on one, you cannot fine-tune on the other. You cannot go from one task to the other. This relates to critical learning periods, and it opens a series of questions with implication to generalization and regularization. To do so, I will first need to say what is a learning task and in what space do tasks live. And the answer has a lot to do with information. Information is in the data, but it is not the data. So I will need to talk about what is and where is the information in a trained model, and specifically a deep neural network. Most importantly, I will talk about how to transfer information from the data to the trained model. Now, there is an asterisk in the word information because there are many subtleties involved in defining and computing information, which I will touch upon in this talk, but I will give you references to papers where the questions are worked out in detail. When we talk about transferring information from one task to another, it is a dynamic process. Part of that transfer of information entails forgetting, and forgetting is what we observe in the initial example of critical learning periods, but it is also related to generalization and to regularization. So I will conclude by arguing that transfer learning requires rethinking regularization, and I will illustrate with an example that shows that regularization in deep learning does not fit the classical Tikhonov story. In the process, I will define a dynamic distance between learning tasks that finally formalizes the notion of task reachability. I will start by describing what I mean by a learning task. So normally a task is specified in terms of the desired output y that the system provides in response to a measured input x. X here could be an image or a piece of text or a frame in a video, and y could be a categorical variable like cat or dog or sailboat, or it could be a continuous variable like the steering angle when driving a car, or it could be the answer to a query. And the map from the input to the output is typically a parametric function p sub w, where the parameters w are inferred starting from a finite collection of inputs and outputs, which is called the training set. So we call y the task variable. And keep in mind that this is not restricted to supervised classification. Y could be equal to x, in which case we have reconstruction or prediction tasks or self-supervision. And Y could be continuous as in a regression problem. But here I will use supervised classification as a prototypical problem for illustrative purposes. The task in a machine learning problem is specified by the training set. When you start training the model or inferring the parameters W, the system doesn't know anything but the training set. So whatever information about the task you have is in the training set. Now, once you're done training, whatever information was in the training set is now in the parameters of the model, because that's all that's left after you're done with training. Of course, you could have very different data sets that describe the same task. If you want to detect cats and dogs, there could be many different images of different size with different context that all train a model to recognize cats and dogs. So clearly the dataset is not a good representation of the task itself. Similarly, there are many different models that can represent the same task because they could have different architecture, different dimensionality, and so on and so forth. So in reality, what we are interested in is not the dataset or the model, but we're interested in the information that they contain. Okay. Now, information is in quote because, as I mentioned, there are subtleties in defining these quantities because the dataset D is not a distribution. You have one dataset. And once you're done training, the parameters W are fixed. So there is no distribution of the parameters. So I will come back to this issue. But for now, the task could be equally thought of as a posterior distribution, which is the true representation of the task, which you have no access to. You could think of the dataset as the task. You can think of a trained model as a task, especially a model trained to overfit. But in reality, we want the information contained in all the above. And ideally, they should be the same. So why do we talk about information in deep learning? Well, when we train a network and we try to transfer information, whatever that means, from the data set to the weights or to the model parameters, what we're doing is we're taking a finite sample of input and outputs, and we're trying to approximate the optimal discriminant, which is the posterior distribution. And we do so by minimizing the empirical cross-entropy, which is an approximation of the expected cross-entropy that has as a minimizer the posterior, which is the Bayesian optimum. Now, the problem with that is that the empirical cross-entropy, which is the finite sum of the log posterior approximated by the model, does not have as a minimizer the optimal discriminant, the posterior. The minimizer is actually a train of delta centered at the samples, which is what happens when you overfit. So clearly, in order for us to really solve the learning problem, we have to modify the loss function because the optimal of the empirical cross-entropy is not the solution we want, and we know that at the outset. So we need to add something to modify the loss function, to regularize the loss function so that we obtain a minimizer of the actual expected cross-entropy. In other words, regularization in machine learning is part of the problem definition rather than the solution, unlike, let's say, in optimization in computer vision, where you want to find optical flow and it's a very heavily non-convex problem and you want to smooth or regularize the loss function. So the question then is, what regularizer should we add to the empirical loss so that the optimal discriminant becomes one of the solutions at least, and so that we can generalize? The answer comes from PAC-Bayes, and the PAC-Bayes bound says that if you want to add something to the empirical cross-entropy such that the solution will approximate the posterior density, then what you need to add is precisely the information that the weights contain about the dataset. One of the renditions of the PAC-Bayes bound says that the test error, which is the expected number of mistakes you made in the test set which you have no access to, so you cannot measure the left-hand side, is bounded from above by some function of the empirical cross-entropy loss, which is what you optimize, plus a terms which measure how much information the weights contain about the dataset. If you can manage to make these two small, then automatically you get a small test error, which is indicative of generalization. So ideally, the loss function that you would like to optimize is not the empirical cross-entropy, but it is the information Lagrangian, which is the sum of the empirical cross-entropy plus the information that the weights contain about the dataset. Now, as I said, measuring this quantity is tricky because the dataset is not a distribution, so it is a finite collection of data, so they have zero entropy. And once you train the model, the parameters W are fixed, and the input-output map is deterministic and therefore has infinite mutual information. So this quantity, the way I wrote it as the Shannon mutual information between the dataset and the weights, is degenerate. But at the end, I will give a reference that will explain how to actually define and compute this quantity. For now, accept the intuitive definition of information, and just notice that per the PAC-Bayes bound, the loss function that we would like to minimize is the information Lagrangian. For those of you who are familiar, the information Lagrangian looks like an information bottleneck. It's the sum of a cross-entropy term and a mutual information term. But this is not the information bottleneck that you read about in papers that refers to the activations as a function of test data, whereas this refers to the weights as a function of the dataset. Now that we know how to define information, we might be interested in understanding how that information that originally resides in the dataset is transferred onto the weights. And so if we plot the amount of information that the weights contain about the dataset as a function of the training epoch, what do we expect to see? Well, maybe something like the blue curve, where initially there is a sharp increase in information, and then maybe there is diminishing return in learning, and so you maybe settle to an asymptote. But instead, what you observe is something like this, where there is a sharp increase in information that the network accumulates in the weights, and that is followed by a decrease in information or forgetting. That is a bit strange. Why isn't information increasing monotonically? Why is there this forgetting? And this is actually not a cartoon, it's a plot of the information in the weights of a ResNet 50 trained on CIFAR 100. And what you see in green is the precision as training progresses. So what this is saying is that after the initial accumulation of information, as the network forgets or throws away information, the precision actually increases, so the performance in the task improves. So I take solace of that as an aging academic in knowing that even as I forget, I might still be learning. And this goes against the basic tenets of information theory. In fact, one of my mentors used to quip that his mother always told him to never throw away information. And here we are, throwing away information apparently as a part of learning. And so is this a quirk of deep networks, or is there a more fundamental phenomenon at play? So here's an example where biologists took cats and apply a visual defect. It could be that they put on glasses that made the world look blurry, or it could be that they put an eye patch, and they put it for a finite window of time, and they started that window of time at, let's say, 10, 20, 30, 40, 50 days. And so what you see in green is the visual acuity measured in normal cats as they develop. And so what you can see is that as the cat develops, roughly reaches steady state in about 100 days. So about 100 days, the cat has learned how to see. But if you apply a deficit in the initial phase of learning, then the cat, even asymptotically, never reaches full acuity. And the effect is more pronounced in the initial period. This is called critical learning period. There is a time during which, if you mess with the data, there are permanent damages done to the model. Now, a deep network does not age. It's not a biological system. The connectivity is set at the outset. And yet, if you apply a deficit, let's say if you train a ResNet on CIFAR10, and during a window of 40 epochs, you blur the images you feed to the network, then depending on when you apply this deficit, you observe that the final accuracy is decreased by an amount that is higher at the beginning of training and then goes down. This is a well-known phenomenon across very many different species and systems. For instance, if I take off my glasses for a month and then put them back on, I see just as fine. But if you have a child who's born with amblyopia and you don't correct it soon, then there's permanent damage done. Now, why am I showing this? Because if I plot the sensitivity to critical period, which I showed in the earlier slide, to the Fisher information matrix that I plot earlier, of course they are in different units, so you have to rescale the axis, but what you see is that there is a qualitatively similar behavior, which is puzzling. There's no suggestion here that neural networks be like biological systems, or in fact the contrary. The fact that they are so different and yet they exhibit a similar behavior is of notice. So the point that I would like to bring up is that there are things that happen during the transient of learning that, if not done properly, result in permanent damage to the system. Okay, both in biology as well as in artificial systems. So there must be some fundamental process at play, and this must be an information process, not a biological one, because neural networks don't have any biology. And going back to the Information Lagrangian, what we see is that forgetting is actually a part of learning, because in order for you to generalize, you have to minimize the loss function, which means that you have to minimize the information that the weights contain about the data set. Of course, you have to do so while maintaining a low empirical cross entropy, so low uncertainty about the predictions. But forgetting is an integral part of learning. So what does all of this have to do with task reachability and transfer learning? I would like to use some of the concepts that I illustrated to give you an example of two tasks that are close by any reasonable notion, and yet you cannot reach one from the other. You cannot fine-tune to the second after pre-training on the first. And this goes back to critical period. These are Hubel and Wiesel, who are considered to be pioneers of modern neuroscience. And on the bottom, you see some experiments that they ran on cats that were born with congenital cataract. And so what they did is they corrected the cataract after, let's say, 50 or 100 or 150 or 200 days. And from that point on, the cat was let roam free. And they would measure the final acuity post-mortem to see how well the cat could see. And so what you see in green is the visual acuity in the normal cat. And as we said earlier, after about 100 days, the cat sees as well as it will ever see. And what you see in blue is the same curve for cats that had their cataract removed after 50 days, 100 days, 200 days, and so on and so forth. And what you can see is that if the deficit was removed too late, then the cat would never develop full acuity. And in particular, if the cataract was removed after more than 100 days, the cat would be functionally blind. So as we said, neural networks are not biological systems. They don't age. They're structurally very different. Yet, what we observe in deep neural network is a very similar behavior. And so these are really two different tasks. Task number one is classify slightly blurry CFAR images. Okay, input are CFAR images that have been slightly blurred, and output are one of the 10 classes. Task number 2 is classify CFAR images. Same inputs, in one case slightly blurred, same output, so the taxonomic distance between these two tasks is 0. Okay, yet the critical period shows that if you remove the deficit, meaning if you switch from task 1, which you can consider pre-training, to task 2, which you can consider fine-tuning, after 20, 40, 60, 80, 100, and 120 epochs, you will never reach the performance that you would if you just train from scratch for task 2. So this is puzzling because you would think that pre-training on slightly blurry CFAR images would actually help you then train on normal CFAR images. And not only does not help you, but it actually hurts you, meaning that you do worse than if you had trained from scratch. This is indicative of the fact that two tasks can be very close to each other. Again, we haven't talked yet about specifically what a task distance means, but whatever reasonable distance you can conceive of, these two tasks are similar, and yet you cannot reach one from the other. And it's not explainable as just the learning rate having a nil to the point where the solution is stuck, because the moment you switch task, you have a different loss function. So there is no reason to believe that if there is a local minimum where the solution is stuck in the first task, that location corresponds to another local minimum for the second task. So when we discussed generalization, we said that in order to achieve it, we need to add to the empirical cross-entropy term a regularizer which reduces the amount of information that the weights contain about the dataset. Now, that term should be in the form of the mutual information between the weights and the dataset. In practice, when people train deep networks, they don't have that additional term, although I'll come back to that later because there are inductive biases in the process. But for now, let's pick a standard regularizer that people use, for instance, weight decay, which consists in penalizing the L2 norm of the weights. And this is one pretty rudimentary form of information reduction. So in the standard regularization picture, what you imagine is that there is a very heavily non-convex loss that around the optimal solution has a lot of local extrema. And in order to avoid being trapped in one of them, you want to smooth the loss function. And you do so with the aid of the regularizer with a coefficient that controls the amount of regularization. So what I'm showing here is an experiment that contradicts that picture. So what you're seeing here is the final accuracy achieved by a network where regularization has been terminated early, meaning that you train for a few epochs with the regularized loss function, and after a few epochs, 25, 50, 75, you switch off the regularizer, meaning that you send beta to 0. So from that point on, the network is unregularized, and in particular, the final loss function, the asymptotics, are unregularized. So if there were local extrema around the optimal solution or an inoptimal solution, they're still there. And what you observe is that switching off the regularizer after 50 or 75 or let's say 100 epochs, and then training with the unregularized loss function yields a result which is functionally indistinguishable from the network that has been regularized all along, which is shown in green. Okay, so basically, the beneficial effect of the regularizer is exhausted during the initial transient. Beyond a certain point, it really makes no difference if you regularize or not. Conversely, let's say that you don't regularize at the beginning and switch on the regularizer after 25 or 50 or 75 epochs. You would expect that because the asymptotics are the same, so the final convergence should be the same. And instead, what you observe is that unless the regularizer is applied early enough, no matter how long you're allowed to train after that, you will never achieve the same performance you did as if you had regularized from the get-go. Literally, there is a critical period for regularization. And this again points to the importance of the transient and the learning dynamics. Now, a legitimate question, which I hinted at to before, is this just because the solution is stuck somewhere? And as I mentioned, there's no reason to believe that there's local minimum before and after this transition because these are two different loss functions. But just to check, you can look at whether the weights move, and so this is a TSNE plot, after the transition, and they do. So that's not as simple an explanation. Now, what does all of this have to do with transfer learning? I will come to that in a second. Let me first show you a plot of the information in the weights during training when we switch off the regularizer at different epochs, 25, 50, 75, and so on and so forth. So the blue curve is when we switch off the regularizer at the beginning. So we train unregularized. And this curve is when we regularize up to 25 epochs, up to 50 epochs, up to 100, 175, and so on. What I discussed earlier in terms of what information to put in the regularizer, I talked about Shannon information. In practice, that is not computable because that requires having a distribution of the data sets, whereas we have only one. What you can compute is the Fisher information, and in principle, the two are different, and the Fisher information can be computed even for networks of size in the millions. And this paper, Where is Information in the Weights of a Deep Network, establishes a connection between the Shannon and the Fisher, meaning that when one is reduced, so is the other. The Fisher relates to the curvature of the loss landscape along the path that we are following with the solution of SGD. So what you see is that when you regularize all along, the solution goes through regions of very high curvature. These are narrow bottlenecks. Before traversing these bottlenecks and entering regions of very low curvature, and even though there are multiple solutions in these minimal flat landscapes, they're all essentially equivalent. So it doesn't really matter which one you converge to. But if you can never make it through this bottleneck because you're not regularized, then you never even get to any of these solutions. And so this also happens in transfer learning. If in going from one task to another, there is a bottleneck and the network is not able to cross it, then you will never get to a good solution. And this is what happens in critical learning periods. I hope that by now I've managed to convince you that transfer learning and the ability to succeed in transfer learning doesn't just depend on how close two tasks are, however you measure close, but also depends on the dynamics of learning. And so we are finally at the point where we can try to define and compute a dynamic distance between tasks that relates to reachability. So I will first mention a few static distances between tasks. My favorite is task-to-vec, which is related to the fact that to measure the complexity of going from one task to another, you measure the additional information needed to learn the second task after having learned the first. This is an asymmetric distance, as it should be, because it's easier to learn how to play the tambourine after you play the drums than the other way around. But again, this is a static distance, and critical periods are a counterexample because ideally you would like it to correlate with the ease of transfer learning. So how do we actually define a distance that takes into account the possibility that two tasks may be nearby but not reachable from one another? I will use an approximation that comes from quantum mechanics, the path integral approximation, to compute the probability of going from one task to another. And based on that, define a dynamic distance between learning tasks. The work is a little bit technical, but I'll give you the gist, which is as follows. So ideally, you want to compute the probability of going from any set of weights, W0 at time t0, to any other set of weights, WF for final, at time tf. So you would like to compute the probability over paths connecting W0 to Wt. And you write this in energy form as the exponential of a functional. And in order to compute this, which is essentially intractable, you assume that there are critical paths along which most paths are. And based on that, you approximate the loss function locally, quadratically, along these critical paths and integrate out the perturbations. And that gives you a total probability of going through that path. And once you do all the calculations, you get an expression that has two factors. The first factor is the exponential of the difference between the information Lagrangians of the two tasks. So that's the static task distance that I mentioned that relates to task-to-vec. But there is also a term here, a factor that is clearly not always negligible, witness the existence of critical learning periods. And this relates to an effective potential, and this effective potential depends on the curvature along the path. And so this adds a drag term that is proportional to the curvature. And so this is a dynamic component of the probability over sample paths that we can use to define a notion of transferability or task reachability. So basically, the probability of being able to reach a task by fine-tuning after having pre-trained on a different task has a component that depends on how far the tasks are, and then there's another component that depends on how likely it is for a path to connect one task to the other. This is what we call the dynamic distance between learning tasks. One point of note, earlier I said that in order to regularize, you should add an information term to the empirical cross entropy. And it turns out that this information term is exactly the one that's added by the effective potential that gets minimized by SGD. The notions that I would like for you to consider as part of this talk is, first of all, the information Lagrangian, which is the loss function that you would like to optimize that uses as the regularizer an information term. We have done work aimed at calculating this information term, and we have work that establishes that even though it's not explicitly there are inductive biases in SGD, as well as structure of the architecture, as well as explicit regularization procedures like dropout or weight decay that reduce the information in the weights and so approximate this entropic term. The information in the weights is really a central element of deep learning as well as transfer learning, because before learning starts, whatever information means to you, it's in the data set, and after you're done learning, it's in the parameters of the model or the weights of your deep network. So it's really important to understand what information in the weights means, and it's entirely non-trivial to define it and compute it simply because the trained network is a deterministic function, so the input-output map is deterministic and has infinite mutual information between input and output. Also, the data set is one. It's not, you don't have a distribution over data sets, which is required to compute Shannon's information. We have done work that establishes a connection between Fisher information and Shannon information for the specific case of training deep networks with first-order stochastic methods like SGD. If we want to understand transfer learning, a basic question is, what is the basic relations between tasks? The simplest is how far are two tasks, and so this is a static component addressed by task2vec. And what I have focused on in this talk is the fact that even that is not enough to understand transfer learning, because there can be tasks that are close to each other, yet there are no likely paths connecting one to the other. And this is shown by the existence of critical periods, and we have been able to approximate the likelihood of joining 2 points. So where do we go next? Clearly, the mechanism for regularization, which are very central to machine learning, because regularization is part of the definition of the problem rather than the solution of the problem, as conventionally in ill-posed problems, really requires additional work. And the transient of learning in particular, the dynamics, is very important, and most of the analytical work is in the asymptotics. And so the transient matter, learning dynamics matter, and I hope that others will join us in effort to understand those. Thank you.